The next question of CodeChef Starters 115 is subtraction sequence 1.
So in this question, we are given with an array called B, which is B1, B2, B3, all the way up till Bm. Right? Size of the array is M. And in this array, they are asking us to perform some operations. Right? The operations that we should be performing should start from I is equal to M minus 1, then M minus 2, M minus 3, all the way up till 1. Right? Now, in every operation, right, in every operation of, let's say, I is M minus 1 or M minus 2 or M minus 3 or whatever, we need to choose a J index. Right? This J index will be greater than 1 and J index will be less than or equal to 1. Sorry, J index will be greater than I and J index will be less than or equal to n. After choosing this J index, we have to replace B of J with max of 0, comma B of J minus B of I. Okay, this is the operation that we should perform. Okay, and when we are performing this operation, it is necessary that we perform the next operation on the updated array. It is not necessary that we have to perform the operations on the original array. After performing one operation, the next operation should be performed on the updated array. This keeps on continuing, and at the end of all operations, the question is defining as f of b, which is nothing but maximum possible value, maximum possible sum of all elements of B array. After performing this operation, all like for this I we have to taken a J, perform this operation. For this I we have taken a J, perform the operation, like this. After performing all the operations, they are defining a term called f of B, which means finding the maximum possible sum of all the elements of B. Right. This is what we should be doing for an array. Okay. Now, in the question, they are saying that if B is given as an array, these are the following operations that you should perform and find out maximum possible sum of all the elements of array B. Right? So basically, we'll be given with an array A whose size will be n. Right? We first have to find what is f of n. What is f of A. Right? We have defined what is f of anything above, right? Which is maximum sum of all the elements of array A after doing all the operations. Right? So once we have found out f of A, then they are giving us Q queries. Right? Every query will give you two integers x, y, where we are supposed to convert A of x is equal to y. And after doing that, A of x is equal to y, we again have to find out f of A. That is maximum value of all the elements, maximum sum of all the elements of your A array after doing all the operations. Right? So after every query, we have to find out f of A value. And we have to print it. Right? And they have also given that the changes that we are doing in every query are permanent. Like it means after one query, when you change the value of A of x to y, in the next query, if it is x1, y1, then this change will be permanent. You will not roll back to the previous value of it. So that is how every query will be changing the array, and after changing the array, we are supposed to find f of A value every single time. Yes. That's the question. Looking at the constraints say that there are t test cases which are in the range of 1 to 4 into 10 power 4. We are given our n value as well as our q value, which are in the range of 1 to 2 into 10 power 5. We are given x value, which is in the range of 1 to n. We are also given our AI value, array element value, and our y value, which are in the range of 1 to 10 power 9. 1 to 10 power 9. Right? It is also given that sum of n and sum of q do not exceed 2 into 10 power 5 over all test cases. These are the constraints.
So in this question, basically, we have these operations. Right? So let us consider the order. we pick I m minus 1, then m minus 2, m minus 3, so on till we go till 1, right? Considering 1 based index. So now let us consider our array B as B1, B2, B3, B4, so on till Bm, right? So now this is our I index values and this is our current array. So now we can observe some things over here firstly. One thing is we know that for a fixed I, we should pick a j which is greater than I and less than or equal to m. Right? Now we know that after picking this, we need to set the value as max of 0, comma b of j minus b of I. Sorry, b of j minus b of I. Right?
B of j minus B of
B of I. This is what we need to set. So now let us put these conditions aside and let us observe two type of things that can happen for any ith index. So now before that, I'll be denoting S as sum of B, sum of original B, given B. So now, can I say that the two type of operations that are happening that could happen are type 1. Firstly, we could remove total sum from S, right? Total B of I from S, the initial sum of B. And type 2 that can happen is we can remove some delta from the final sum of B. And that delta will be in the range 0 to B of I. This is what the delta is. So
Now,
the,
why we are saying that this delta will be removed is because if we have a look at this operation,
yeah,
when we pick any j,
yeah,
right, and when we do b of j minus b of I, their difference can be 0,
yeah,
the difference can be positive, the
positive,
difference can be negative.
Negative.
The question says that we'll have to convert b of j into b of j minus b of I or 0, whichever is maximum.
Whichever is maximum.
Right? So if the difference is greater than 0, then we can say that b of I is getting completely subtracted.
Completely subtracted.
If the difference is negative, then we are replacing it with 0. It means only b of j is getting subtracted, not b of I.
Not b of I.
Right? It's a portion of b of I that is getting subtracted.
That is the reason.
That is the reason there are two scenarios over here. Where first scenario is completely subtracting b of I from S. And second scenario is subtracting a delta which is in the range of 0 to b of I.
0 to b of I.
Right. Now, why are we subtracting that from S? Why not from b of I, b of j? Because we are supposed to find the maximum sum of the entire array. Right. So if we are replacing b of j with b of j minus b of I, at the end, from sum only we are subtracting. Right?
Yeah, from sum only we are subtracting.
That is why we are, instead of individually subtracting b of I from b of j, we are taking a total sum S, and from that sum S we are subtracting b of
I. So these are the two partial cases that are happening. So now let us make one more observation. If we want to subtract b of I from any available b of j, my claim is it is always better subtracting b of I from the minimum most element. Right? Why? Because if we subtract b of I from the minimum most element, that could result in a smaller portion of subtraction in the total sum. Right? So we can pick an example. Let's say I want to subtract 5 and I have 2, 1 and 3. Then if I subtract 5 from 1, then my total sum is initially it is 11, right? So from 11, if I subtract 5 from 1, only 1 gets subtracted if you observe. Right?
Yes.
If I subtract from 2, 2 gets subtracted. If I subtract from 3, 3 gets subtracted. So here subtracting from 1 is always beneficial. So that is why to maximize our chances to get the maximum sum, we can subtract the current element from the smallest element that is available. Right? And now there is one more observation. The observation is a configuration which could give us, which could maximize the final sum would be, let's say we have some index I, and this is 1, 2, 3, so on till index I plus 1, so on till index M, right? So if this is my configuration, then my claim is there will exist there will exist a point I if we want the maximum final sum, where we will subtract all this part from I. Basically, let's call this as the prefix part and this as the suffix. So from prefix part, we will be subtracting, basically in the prefix, what we do is we'll be subtracting from B of I, we'll be subtracting so on plus B of 1, right? So like I'm assuming that this I will be the smallest over all the operations that we are doing here. And why only subtracting from B of I is we just saw. If I subtract 1 from this and 2 from some other thing, is it beneficial?
No.
No, right? Why? Because if I subtract 2 from some other thing and 1 from some other thing, the subtraction, we are distributing the subtraction. Instead, if we concentratedly perform subtraction on a single element, that would reduce the element evenly. So that is why it is optimal to subtract from only one element, and we are and like this I will remain the minimum most, assuming this I will remain the minimum most after performing all the operations in this.
I will not be minimum. The B of I will become.
Yeah, B of I will be the minimum most by performing the operations in this order. That is, first B of I is minimum. Then after subtracting B of I minus 1, B of I and B of I minus 1 became minimum. Then when we are choosing for I minus 2, B of I and B of I minus 1, that will be the result over here. That will be the minimum when we subtract B of I minus 2 from B of I minus 1 and B of I minus 2, and so on. Right? So this is the structure that it has. And in the suffix part, we are assuming that all the values from B of I plus 1 plus B of I plus 2 plus so on plus B of M minus 1, whatever this part we have, that part will completely get subtracted from the suffix, is what we are assuming. Right? This will completely get subtracted, whereas the prefix part will partially get subtracted, is what we are assuming. So this kind of scenario can exist, and that is because you guys might think, why not partial case occur here, right? If in case partial case occurs, that means some element is getting set to 0, right? In case if any element gets set to 0, that just implies that this element will be the ith point from which we start subtracting whole prefix, this whole prefix. Right? So that is why, for sure, if there exists a I from which we are subtracting all the prefix, in the suffix part there will never exist partial intersection. That part will completely get subtracted from the sum. So we just proved this now. Now we know that there exists a I such that there exists a beneficial I such that subtracting whole prefix with that I would maximize our sum, final sum. Right? So now let's see how we can calculate the value for this fixed I.
Now, when we are subtracting everything from ith index, right, it is only the prefix that is getting subtracted, not the suffix.
Not the suffix.
The suffix, let's say I plus 1, it is getting subtracted from some value after I plus 1.
Yeah, after I plus
1. Right? And here we are assuming that there is no index after I plus 1 where subtraction is partial.
Yeah, subtraction
we're assuming that all the values which are getting subtracted
is
are completely getting subtracted
from the prefix. So with this, let's just calculate. Let me write out here. Here, complete subtraction is happening. And here, partial subtractions. Subtractions happen. Now let's formulate how we can formulate this. So, if in case this condition isn't given, setting the value to 0, B of j minus B of I. If this is not given, if this setting 0 is not given, then can I say my sum will be S minus B of M, the last element? Final, like for sure will result in this sum, no matter how we perform operations, right? if in case this 0 is input. Then we can see that the value, if we perform, if we just simplify this, it becomes B of M. Now, from this B of M, we should add back some delta, right? So the delta that we are adding back, let me call that delta as delta. Now let's see how we can calculate that. Basically, we'll add back the delta which is going negative uh, when we are subtracting the prefix part, right? So let us call the delta as plus B of 1, right? This is my delta. In case this is positive, then the delta would be 0. We'll consider the delta is 0. Why? Because already, if it is positive, the subtraction is already done here. And if it is negative, then the delta would be absolute of B of I minus plus B of 1. Right? If it is negative, that is because whatever negative part we have, that is the thing that we subtracted extra, but that could be set to 0 because here we have 0. We can set it back to 0. So that is why this negative delta, this is negative, and this negative delta that we extra subtracted will add it back. So that is why we can add back the delta. Right? Now, for a fixed I, this is for a fixed I, right? For a fixed I, we found out how we can calculate the best final sum that we can get. Now, what we do is, we don't know which is that I which will give us the optimal sum. Right? So we'll try it for each and every I. Let's say this is my I. Now, when we are trying for each and every I, you guys might think that we don't know that I is correct, that I is a satisfying I or no. If that I is not a satisfying I, then there can exist partial intersection here, right? But though that partial intersection exists here for an invalid I, what we do is we are subtracting the sum of all the elements. Right? Here we are assuming it's complete intersection and subtracting it. So uh, that means if partial intersection exists, the actual sum will be more than the current sum that we are getting. Right? Why? Because we are in the current sum, we are subtracting them completely, but actually they should be subtracted partially. So because for an invalid I, we are subtracting even more. Ultimately, whatever sum we are getting, that will be some sum which is smaller, right? Smaller than the actually performed sum. So that is why for every fixed I, when we pick the maximum, like for every fixed I, we are picking the maximum sum that we are getting. Right? So among all these sums, the whenever we fix the invalid I, we got some sum which is smaller, right, than the actual sum. All such sums will get ignored as we want the maximum sum. So there will be a valid I for which the sum will be maximum, the final sum will be maximum. And when we are picking the maximum among all the set of I values, that sum will pop up, right? That sum will have the maximum sum, and that will be our result. So that is why we can just fix I, assume the suffix as the part that is completely getting removed, and prefix as the part that is partially getting removed, and we can just calculate what will be the result. So ultimately, answer would be for all I in the range 1 to m. Okay. Answer is maximum of B of m plus the delta. For every I, we calculate the delta. So maximum among this will be the answer. Now the thing is, for every I, like if only array A is given, we can just do it in OM. Right? We can, for every I, we can calculate the value. But here even queries are given. So for every query, we can't update A and recalculate the answer because that would cost us, for every query, we'll be iterating a loop of n, right? That will cost us Q into, which is inefficient. According to the problem constraint, we are not allowed to do a q into n. We are not allowed with a q into n solution. So now let's see how we can optimize that. So before moving on to the optimization, let's understand the current observations and the formulation that we did by dry running on a test case. I just took the sample. Let us calculate the answer for this array if we do the same process. So here I is 0. Okay, let me consider it 1 base. I is 1, 2, 3, 4, and 5. Right? Now, if in case my I is 5, let's come from reverse. In case my I is 5, then what will be my value? Can I say what is the total sum first? S is 10, 18, 25, 34.
34.
So 34. Now I need to, okay, 34 is the total sum, but we don't need the total sum. We just simplified it and it will get simplified to B of M, right?
Right.
So B of M here is
9.
9. 9, and we should add some delta. Let's calculate what is the delta for it. When it is 5, the delta will be 9 minus 8 plus 5 plus 5 plus 7. Right? So the delta is
25, 9 minus 25.
9 minus 25. So which is nothing but minus 16. Right?
Yes.
So here it is minus 16. So we add, because it's negative, we add absolute value of this, which is 25. Now for I is equal to 4, it is 8, not 8, 9 plus
Finding the delta.
finding the delta. So delta is 8 minus 7. So this is minus
9.
yeah, this is minus, yeah, minus 9. So this would just be absolute of minus 9. Right? So that is nothing but 18. I is 3. Then it would be 9 plus. So this is absolute of minus 7, which is nothing but my 16. When I is 2, it is 9 plus minus 7, which is nothing but absolute of minus 7, which is this is 11.
Wait, 5 minus 7 is minus 2.
Yeah, I mean minus. This is 11.
Okay.
When I is 1, then it would be 9 plus 5 minus. But here, if we see, this is a positive one. So when we formulated S minus the value, we already subtracted the positive part. Right? So that is why this would turn out to be 0. If it's positive, then it's 0. So for this, it's 9. So among this, the maximum sum is 25. So by performing this process, the best final sum that we can get is 25. Now here we are doing this in right. For every I, we are finding out what is the max value. But for every query, we can't do this because there are queries. For initial A, we can just find the answer in this way in OM. But for every query, we can't do this. So now for every query, let's see how we can do it. We can answer every query in log. For that, the prerequisite is you should know segmentary range update, that is segmentary lazy propagation. We'll be using seg3. So people who are not familiar with it, you guys can pause it over here. Then learn segmentary lazy propagation and then continue from this part. Then it would be clear. So here, let us look over the segment tree structure. Firstly, I won't explain how we are implementing it, as it is just a standard range update segment tree, range update with minimum query segment tree. So basically, st of, let's say we have two functions, update, st of update of L to R, comma X. It takes in three parameters, let's say. What will this do is, for every element in the range L to R, it will add it will add a value X. This is what it does when we call this. And let's say we also built a function query of L to R. This will tell us what is the minimum value that we have in the range L to R in the segment. So it returns us the minimum value. Now let's see how we can use this segment to calculate our answer. So what we can do here is, firstly, let us build basically for every I, let us look at the formula that we derived. For every I, the formula is B of M. This B of M is always stable, right? For everything B of M we add, plus we add some delta. Now we are building segment tree for this delta. So what happens is segment tree node of I, like ith node, basically ith index in segment tree will store what is the delta of I. What is the delta of I? If we know this, then it is always optimal to pick the minimum most delta, right? Why? Because more minimum the delta is, more negative it could be. So that is why we'll pick the minimum most delta. As we know, minimum most delta will maximize our answer. So that is why we
will add that absolute value.
Yeah, we'll add the absolute value of that minimum delta. So we are adding the absolute. And we should ensure one more thing, that minimum most delta shouldn't be positive. Right? If it's positive, we add 0. So if it's positive, answer is just B of M. So now let's see how we can build this. So the way we can build it is, let us iterate over I in the range 1 to M. Right? Now what we can do is, I'll just call update I comma B of M. This means I'm setting ith index value as B of I, right? And how will this B of I affect higher indices? In delta, we are basically calculating B of I minus B of I plus 1, B of I plus 2, so on. Right? Sorry, B of I minus B of I minus 1, B of I minus 2, so on. So that means this B of I will contribute in subtraction for all the deltas of B of I plus 1, I plus 2, I plus 3, so on till B of I. So that is why what we can do is, we can update I plus 1 till M with minus B of I. Right? This will subtract minus B of I to all the elements in the range I plus 1 to M. Now can I say, in my ST segment tree, I have all the delta values for every ith index. Right? All delta values are available. Now I just need to query. I just need to query for the minimum most delta. So for a fixed I, so we calculated this for B, fixed B array. Now for a fixed B array, what will be the answer? Can I say for this B, my answer is B of M plus absolute of, okay, I'll just write it as st dot, okay, I won't write it over, query of, it is considering all of them, right? Index 1 to M, absolute 1. So basically this is our query, and we add up absolute if this is a negative, right? Otherwise, we consider this to be 0. So this way we can just query from the segment tree to get the minimum most delta. And if it's negative, we can add it. This will be my answer for the fixed B, right?
Fixed I.
Fixed I. I mean, if my B array is, if my
Okay,
initial B
yes.
array is this,
Yes.
then this will be my answer. Now let's see how we can handle queries. Now we have Q queries, right? Now the changes are like, we should make x index, we should change x index to y, value y. So that means, can I say that the way I need to update it is my previous value? Okay, we are making changes to x index, right? In my previous case, I added b of x to my x index. Now I'll subtract it because I should remove my previous answers. So I'm to remove the previous value. I'm subtracting it from this index. And what I did is I added, basically I subtracted b of x from all the indexes in the range x plus 1 to m. So now we should remove that. So to remove that, I'll just update the indexes from x plus 1 to m with b of x. Right? Previously I subtracted, now I'm adding. That means it's just nullifying it. Right? Now what we can do is we can modify our b, because we should modify it to this. And then we can just add back this contribution. We subtracted the previous contribution and adding back the current changed contribution. So x. So this is the updated b, and it will even contribute for indices x plus 1 till n. And we should subtract this, right? So with this, we could just change the whole configuration. So this will take a login, this will take a login, this will take a login, this will take a login. Basically, update is login and query is also login, assuming that. So now, ultimately, now we have the updated configuration of the array. So answer for this would be b of m plus this updated segment. It is the same. We can just query for the minimum value. Right? This should be negative. Then only we should add. Otherwise, this whole thing will be 0. So this will be the value. So basically, in the segment tree, we are maintaining delta. And for every query change, instead of recalculating complete delta, we are just calculating the part which is recalculating the part that is required. So here, for that, we just maintain segment tree which stores all the deltas for every index. And we are just updating for a particular point change. We are just updating the indices that gets affected with that change only using the segment. So once we update it within login, will be having the updated configurations answers, updated configurations deltas in the segment. We can just query the minimum one. So this way we can just use a segment tree and optimize Q into N to Q into login. So if you look at the time complexity, it would be big of constructing segment tree will take us N login, assuming N is the size of the array. Here we took M as the size, so I'll just mention it as M only. Assuming M is the size, it would be big of M log M, right? Plus Q into M log, not M log, Q into log, because there are M indices in the segment, so it takes log M. And if we look at the space complexity, we can say it is big of M in the worst case. Basically, seg tree will take a space of big of 4 into M. In big O notations, we can say big of M. It takes 4 into M. In big O notations, it's big O. So all these are per test case. And if you look at the worst case, it is mentioned that sum of N and Q over all test cases won't exceed 2 into 10 power 5. So basically, in our case, N is M because we used M as the variable. M is nothing but size of the array. So in the constraints, whatever N we have, that is M here. So that will be in the range less than or equal to summation of M and Q will be less than or equal to 2 into 10 power. Right? So now we can assume a worst case where we have one test case. M is 2 into 10 power 5. Q is 2 into 10 power 5. Right? So size of the array is 2 into 10 power 5 and queries are 2 into. So this is sufficient enough to pass in 1 second, as it would just cost us 2 into 10 power 5 into log n into this. It would approximately, if you substitute the extreme values, it would approximately go till 10 power 7 in the worst case. So that is sufficient enough for a 1 second TM. So this way we can solve the problem.